going to work. All right, so this should be coming through, and welcome for those watching in the future. So we are in PO6 and we are going to cover a few things. So a couple of things that we're going to be looking at. We're going to be looking at your math investigation. We're going to be looking at your homework as well. So for those of you who aren't here, or those of you who are here, hi. Everyone say hi. There we go. Okay. You can all watch back in the future and you can all say, that was me. I did that. Okay. But otherwise, all right. So let's just have a quick look. Sorry, I got too many tabs and too many things and too many screens. So let's have a quick remind ourselves of what we've said. So we've got a short week, and so for some of you, it's shorter than others. Expectations. All right, expectations for you guys. So you have another week or so into a week from today, and a few hours for submission of your draft. You are welcome to hand up a draft earlier for your polynomial investigation. The final is due on the 30th. Okay, but my expectations is that I would like to see what you have done by the end of today. So you have a few hours to upload something that you've been working on. And I will check the next couple of days to see whether I'm satisfied with your progress or not. Other than that, we've also got, here's the homework I said, so chapter 5A and B. Now, these are pretty easy homework, but I will go through it briefly and I will explain a few concepts. So we'll be doing a little bit of that, do a few questions. We'll start off with that, and then I will show you part B of the assignment. So bear with me, I'm going to do this in one take because I can't be bothered editing. All right, because it takes too long. All right, so let's go to our textbook. Let's go to my tabs. All right, here we go. So this is 5A. So we've already covered a little bit of this stuff. Now, you remember from a long time ago, one measure of angles using degrees. If you go back all the way onto yourself, you've completed one full period, and that is 360 degrees. But we've been graphing sine functions, and we've been using radians instead. We'll see why radians are preferred later on, because they're a more natural unit for some purposes. But one full circle is 2 pi radians. We'll come back to that concept later on. All right. So the radian measure of angles. So you see an example here. We've got a part of an arc. There's your arc length here. 1 radian. If you have a radius of part of a circle and you only go 1 radian, well, it just so happens that the radius of that slice of pizza and the arc length of the cheesy crusty edge has the same length. Isn't that cool? Everyone say that's cool. Okay. All right. Don't need to ham it up too much. Come on, guys. It's only math. All right. So insofar as that, all right. So that's where this kind of concept comes from. Now, if you go around a semicircle, you've done 180 degrees or pi radians. Now, we usually don't bother with unit for radians, but if you want to put one in, put a little C symbol for radians. Radians is a natural unit, so it doesn't actually need a unit. But in this context, just so we don't get confused between degrees has a little circle, and radians has a little C. Okay, now here's a simple table. How to convert from degrees to radians? Times by pi, divide by 180. You got radians. How to convert from radians to degrees? Times by 180 divided by pi. Easy peasy. Okay, so let's look. This is what you'll be doing. So basically, you're just working with fractions. All right, so convert radians in terms of pi. All right, now, okay, I'm thinking of how can I, if I was to write an example here, maybe I'll just show them. All right. Okay, let's have a try of something. Now, sorry, the technical issues. I'm going to change what I'm sharing. I'm going to share a whiteboard space. So those who are watching will see a blank screen. Those who You can also open up your textbook and watch along with it, but you won't be able to see the questions. But that's okay. I'll write the questions. All right. So let me just see if I can do this. All right. Let's do an example. Convert from 2 radians in terms of pi. So I'm going to do question 1. Now I use the mouse with my right hand, so this is going to look very ugly. Apologies for that. All right. So in terms of that, so 1a, I want to convert 90 degrees into radians. So what do? I times by pi. Okay, that's all right. I've already marked it down as late. Say hi to the world for us. This is now modelized. Oscar was late today. Okay, there you go. Okay, all right, that's good. That's all right. And you managed to make it to math. So that's for those who weren't in class. So also they're doing the best of both worlds. So there you go. Okay, all right. So let's have a look. So we're converting degrees into radians. So we're timesing by pi on 180. Okay, well, now, a lot of cases we can actually simplify stuff. So actually you can, 180 is 2 lots of 90. So you can change that to 1 there. So you've got the simple way to write that as a fraction is pi on 2. How cool is that? Pi on 2. Easy peasy. All right, convert from radians into pi. Let's do another one. All right, how about, let's do H. 270. Okay, we're going to convert that into radians. All right, what do we do? 270 times by pi on 180. Okay. Now, if you work that out, you can reduce that. Both of these are multiple of 90. So if you think about that, if you divide by 90, 270 becomes 3, I believe, and that becomes 2. Okay. So that is 3 pi on 2. Okay. So reduce it down, and you can see you can actually do that. You can write them in terms of pi. For other questions, okay, if it says convert to radians, create the 3 set figures, just do it on your calculator. I think I don't need to explain that much. I'll do another one. Okay, so I'm going to clear all my drawings. All right, now I'm going to do the reverse. I'm going to convert 2 degrees. All right, let's take pi on 5. Okay, to convert that, I do the reverse. I times by 180, and I divide by pi. Okay. Well, if I cancel out, okay, if I take out the common factor of 5, now a little trick about 5, you divide by 5 is same as divided by 10 and times by 2. So 180 divided by 5 is 36. Okay, you can also cancel the pi's. So basically that is 36 degrees, I believe. All right, and put your little degree symbol there. Okay, so this stuff is pretty easy, isn't it? Let's move on to something more interesting. Okay, I'm going to go delete that, and I'm going to share back. Okay, let's go back to this page. All right, so match each angle with the correct diagram. It might be easy for you guys to, when it comes to this stuff, convert to something you're more familiar with. So the ones at 70 degrees, so 70 degrees, anything in radians, anything that's not has a degree symbol, pi on 2, assume that's radians. All right, we actually worked that out before. That's, I think that's 90 degrees. And yes, if it doesn't have a symbol, you can assume that it's a radian. So you see that 0.5 is not mentioned, that's radians. All right, and if you figure that out, okay. So convert that, and you should be able to match it to the one that's the most appropriate with there. All right, and you can do that for yourself with what I've shown you so far. All right, now the next thing I wanted to show you is an application to this. So we're going to look at arc length and sector area. All right, so arc length is how, so if you've got a slice of pizza, So you can see here's a slice of pizza. All right, so a slice of pizza is basically part of a circle. So you have a circular pizza, you put into slices. All right, so the arc length is the measure of this arc here. The sector area is the area of your pizza slice. That makes sense? Okay, segment, don't worry about that for now. We need to cover the area of a triangle with using angles to actually determine that, but we'll save that for another day. So really all we're going to be doing is we do sector areas and arc lengths. All right. Okay. So moving on. All right. So in terms of arc length, you have a very natural formula here. For degrees and radians, arc length equals L equals theta times R. Now that's if theta is in radians. You see how simple that equation becomes if it's in radians. If it's in degrees, well, you have to carry out this conversion. So if you got theta in degrees, so you can use one or the other, but if you're working in radians, you have a very natural equation. Just to take the angle in radians times by the radius, you've got the arc. Okay. All right. Area sector. So if you can't get the area sector, if the angle is in radians, is half theta r squared, radius squared. If it's in degrees, theta divided by 360 times pi over r squared. Okay. And most of this stuff is just calculations. This is why I said this stuff for homework. So use the appropriate formula, come up the arc length and the sector areas. I'm going to, maybe I think I will go through one problem solving exercise. I'll do, because there's probably anything challenging here. So some of you have to work backwards, but all right. Yep, some of those problem solving might be a little bit tricky. Maybe I'll take one of these. Let's do question 8. All right, so what if I was to, all right, let's do snip. All right, show you a little trick. All right, I can't keep 2 windows up at once while I'm recording, so I'm going to copy that and I'm going to share my, let's see if this works. I'm just teaching myself stuff as I go. All right, let's share the whiteboard again. All right, let's get rid of that rubbish. And let's see if I can just do a paste dump. Nah, didn't work. No, okay, no, it doesn't like that. But what I could do, let's just open up Paint. That'll work. Okay, there we go. So now it's basically the same thing, but I need to share that now. Okay, Paint. There we go. All right, so I've got my diagram. I'm just going to, so that's the only thing you guys watching at home can see, but I'm going to keep the question up for everyone else. All right. So part A, okay. So we got this diagram here. All right. So what do we know? The end of the wall of a brick building is a shape illustrated where the center of the arc AB is at C. Okay. Find alpha to 4 cent figures, find theta to 4 cent figures, and find the area of the wall. All right. So I could basically break up this wall into a sector area that goes from A to C to B and around. And then I've got these 2 triangles to work out the rest of the wall. So I don't have to work out the segment. What I do have to work out is, okay, I need to work out alpha, 4 cent figures. Okay. Now, where's my tools? All right. So let's see how I can do this. Okay. So now, if that's 30 meters across, that's 15, and that's 15 centimeters. All right, let's do it differently. Nope, not as good. All right. Let's put them in 15. And that's 15 as well. Yep. Okay. All right, so I've got those lengths. I've got that's 5. I can work out this using a few ways I can do that. So I'm working at alpha first. Now this is a right angle triangle. So I could work that out with Pythagoras or with SOHCAHTOA. I've got those two sides and I want to work out this angle. So if I've got the opposite and the adjacent, just remember your trig ratios. Yeah, and yeah, adjacent would be, if I look at this triangle here, so if I use the inverse tan function, okay, equals opposite, which is 5 over 15. That will give me alpha. Okay, now, okay. I'm just going to pull out, where's my TI? All right, we all should know how to use the inverse tan function for the purposes here. I haven't got my calculator loaded. All right, so let's go quit. Okay, so just do inverse tan of 5 over 15. Okay, let me just check if I've got that in now. I've got that in radians. Just be aware of that. Because yeah, you usually used to doing, if I do that in degrees, do that again. If I've actually switched over to using radians. Okay, in degrees, so most of you are used to working in angles in degrees. Okay. All right. So that was 18.4. I'll just round it through some figures. That's 18.4 degrees. Okay. Then that's there. So that's 18.4. And that's 18.4. Okay. If those two angles there, that angle there is 18.4 and that one there is 18.4, how do I work out this one in the middle? How do I work out theta? How do I work out this one? Subtract from 180, yes. All right, so let's just do 180 minus, I'm just gonna do with this 2 times the last answer. Whoops, 180 minus 2 times last answer gets us 143.13. I'll just do 143.1. That will do. Okay. All right. Now, I want to work out the area. How do I do that? Well, we've just learned how to work out area of segments. So that segment's in here. Okay, well, I just filled in. Okay, we've also got these triangles. Now, you should be able to do the triangles. Okay, the triangles, or let's just call it, okay, let's just say it's sector, do typing. So yeah, people can actually read this. All right, sector plus 2 triangles. All right, well, what's that? Okay, get my thing out. Well, let's work out the sector. All right, if I do that with the formula, all right, actually one thing I'm missing, one thing I need is a radius. Okay, now to get, because you need the radius, you need those lengths for your that. Now that can be done with Pythagoras. So if I just call that R equals the square root of 5 squared plus 15 squared. Okay, there we go. Let's make an approximate of that. All right, square root. Keep forgetting what using my thing. All right. Square root 5 squared plus 15 squared equals 15.81. Okay, So that's that length there. You need that to work out the sector area. That's why that's important. So, all right, let's just put it down here. I'm just going to put everything and just kind of punch it in. If I've done everything in 3 simple figures, I should get it about correct. All right, so the sector is, okay, you need because we're working in degrees, you need the degrees formula. That is 143.1 over 360 times by, because this is a ratio of your area of the circle formula. So you got your pi r squared, by your r, we just worked that out, is 15.81. Okay, squared. All right, that's your sector area. Now you've got 2 triangles. So 2 times by. Now, the easiest way to work out these triangles is half base times height. So 2 times 1/2, well, you don't really need that anymore, times base, 15, times height, 5. Boom, done. I'm just going to jam that into the calculator and see what it does. All right, so bracket 143.1 divided by 360 close bracket times by pi. Where's pi in this thing again? Oh, there it is. Pi times by bracket 15.81 bracket tilde 2. All right, plus, now you don't need to write 2 times 1/2. You can just write 15 times 5, which I've just done, for those who can't see that. And I just typed something else. No, I didn't. Good. All right. Hopefully that's a correct answer, or at least it's the correct method. I might stuff something else. So 387 square meters. Okay, that should be about right. Okay, that's as much as I'm going to do insofar as 5A and 5B. So try this stuff for yourself. The earlier questions are quite easy. The problem-solving ones you have trouble with. But if you are having trouble with those are at home. All right, let me go and share back. Go back to there. All right. So, okay. All right, yeah. If you got any problems, just you can type your question in here and say, "Sir, sorry, Mister, can you please do question 9 or something like that on page and I'll do that in class next lesson. I don't know, or maybe someone has a solution. Okay, but I'm going to pause this recording, and if you're watching from home, you will then see the part about the assignment. So I'm going to pause for now. All right. Resume recording. All right, so recording again. We are now looking at part 2 of the assignment. All right, so in part A, you investigate using appropriate graphing practice 3 polynomials with 4 distinct linear factors. And the next part of it, you actually went through and you did 5 distinct real roots. All right. So in this case, in part B, we're going to be investigating 3 linear polynomials with a squared real linear factor and 2 distinct real linear factors. So we're assuming that we've got this kind of form. We've got alpha, which x minus alpha squared is our squared factor, 2 distinct real roots. And 2 linear factors, x minus beta, x minus gamma. These 3 cannot be equal. If they are, then you get a whole different shape. And then you can use, you can look at what happens at degree 5 and beyond as well as part of the investigation. Look at that. So you have a squared factor and then you have extra linear factors. All right. So just going back to I just want to refer to that. So the first part of the assignment, at least the quartic parts, I've only graphed the quartics here. You did ones that look like question 1. It could have been upside down, but basically it cuts 4 times. What we're looking at now is we're going to be looking at things that look like question 2. So it cuts 2 times and touches once. So we have 3 factors. So let's have a look what we can do with that. So I've gone and put up, okay. So here is the one that has 4 linear factors. I'm going to change this so that I'm going to make W, I'm going to get rid of, actually, you know what? Let's make that the squared factor. So I'm going to have a repeated factor. So I'm going to get rid of phi and I'm going to change that to W. Okay. So then basically, okay. So phi doesn't matter. See, that doesn't change anything anymore because it's not graphed. All right, it's not part of the function. But you can see I have a repeated root at W. I mean, I could just replace that with W squared. Oops, nope, not like that. Like that. Yeah. So yeah, same thing. It's repeated. But if I just undo that, yeah. So what does it mean when you have a squared factor? It means you have the same factor again. It means, okay, it means we do have 4 factors, but one's repeated. So you have the same value. All right. What does that mean here? Well, at W, that's at x equals 2, that's where it touches. So in my case, it's in the middle. So I can move that around. That just changes where the factors are. But the question is, is that going to change the number of, okay. Yeah, also, yeah, if I move it so it's on the same number as another one, see, that's a different shape. That's where W equals 6 and alpha equals 6. That one doesn't count because that is a repeated factor to the power of 3. So we're not going to count that one. So I have to actually move that away. So there we go. All right. Okay. But if I play around with that, I can get, okay, so in any case, the W factor is always going to be touching. You see that's always touching the x-axis, but not passing through it. And we cut at the other 2. So I can move those around. I can move that over that side. I've always got one touching, always got one cutting. All right. All right, regardless. So let's go through and count our inflection points. Okay. All right, so I've got my tangent function here. I can move that across. All right. Let's just do it from 0. Okay. All right, and I'm going to change that. Okay, so remember the way we go about doing this. So what's that move past? Let's count how many times it becomes horizontal. All right, so starting from 0. All right. 1, 2, 3. So 3 stationary points there. But again, you kind of picked up already that the stationary points are hills and valleys like these. All right, so 3 stationary points. All right. Now, the way to remember to do the inflection points is you watch the animation. Watch how many times the line reverses its direction of turn. So I've sped that up a little bit. Let's see if we can do that. Okay. Right, turning clockwise, anti-clockwise, 1, and turn back again, 2. So we have 2 inflection points. Well, that's more or less what we saw for part 1 as well. All right, but let's have a look if that's consistent. You'll be playing around, you'll be changing these numbers, you'll be looking at other values. So change these around until you see if you can find something different. Okay, so we've got a different one here. Maybe let's actually move that. Let's move these all. Okay. All right. All right. Okay, so I've got my squared factor now on the left-hand side and on the middle. Does that make a difference? We seem to have 2 hills and a valley, and we seem to have 2 inflection points as well. So you might see a common feature about these ones. Okay, well, what happens when we go to order 5? So I'm actually going to introduce a new linear factor. Okay, so x minus phi. Okay, I I'm going to make that a smaller number as well. Let's make that 100. Okay. Nope, too much. What have I done? Oops, not there. There. Let's make that. Okay, that looks a bit healthier. All right, so let's have a look at our order 5. Now we see it touches at, okay, we've got the squared factor is the one that has the W, so that's at 1. I have linear factors at 8, at, make it 5, and we'll put that 1. That's also at 8. Let's put that somewhere else. Let's put that at 5. Yeah, make sure none of these ones are repeating. Okay. Let's put that at 7. Okay, maybe a little bit, we'll ease up a little bit on that. Okay, that's a bit more. Maybe we'll go to 50. Okay, there we go. So there's our order 5 polynomial. It has 1, 2, 3 linear factors and 1 repeated factor. Okay, repeated factor at 1, linear factors at x equals 5, 7, and 8. Okay, let's go count the number of stationary points first, and then we'll do inflection points. So again, what's the animation? So watch how many times it becomes horizontal. 1, 2, 3, 4. Okay, 4 stationary points. Now watch how many times it reverses its direction of turn for the inflection points. 1, 2, 3. All right. So that's pretty much, you might notice a similar trend with what you've observed for part A. So looking at this, so now we're introducing 3 real polynomials of squared factor, linear factor, 2 distinct linear factors, Present you an information table above. Okay, yeah, it's order 5. And you can go to order 6. You might see a pattern that's going on there. So degree 5, degree 6. Could it be, if they have these sorts of relationships, could it be the order of the polynomial is equal to the maximum number of factors, then 1 less for the number of stationary points, and 2 less for the number of inflection points? Because what we're seeing is if we have an order 4 polynomial, we can have 3 stationary points and 2 inflection points. If we have a degree 5, we have a maximum of 5 linear factors, 4 stationary points, and 3 inflection points. That might be something that you observe. If you observe it, you can write it down and you can make that conjecture. Now, with part C, okay, I think I will save that for a future lesson next week. So this is going to be the end of this recording. All right. Okay. Anyone want to say goodbye to the world? Bye. Bye.